Hello everyone. This is the last subject that I'd like to discuss with you in this semester for the mechanics of material class. The last subject is buckling. Buckling, and in other words, we call this problem is stability problem. Stability or instability. In 우리말 we call 안정, 불안정. Okay, especially although there are many different kinds of stability problems, but here we'd like to talk about the stability problems for columns, 기둥 좌굴. So buckling is called in 우리말 좌굴. The stability, or especially in structural stability. in 우리말 구조 안정성. Okay, 구조 안정성. The instability means 불안정성. Alright, so here are the contents of my talk today. After the outline, we'd like to talk about the Euler's buckling load, and then the effect of different boundary conditions regarding the buckling load. Okay, before we talk about some mathematics involved in this buckling subject, so let's talk about some simple examples to understand the problem. First, let's imagine that we have a hill, and then we'd like to put our bike in 3 different positions. So of course, if you put bike here, so everyone understand that. So we can have equilibrium, and then even if we put just the bike without supporting anything, so my bike would stay there. But what's gonna happen? So if you put our bike on position 3, and then because of the equilibrium condition on point 3, we can satisfy the equilibrium. I can put the bike on top of the hill. The problem is if we apply a little perturbation to the lateral direction, then my bike would lose the stability, and then it's going to move downward. But in the case of point 2, even if you apply small perturbation in the lateral direction, my bike on point 2 would find its equilibrium position. Now how about point 1? In point 1, there is no equilibrium, isn't it? Yeah. So my bike would move down to find its equilibrium position. So here, this point, we would like to say this point is not in equilibrium. These two points, they are in equilibrium, which means, even if we consider same problem, there may be more than one equilibrium status. So confusing? Let's consider another situation. Let's consider 2 balls, and then I have an orange ball on top of white balls. Okay, look at the force here. The force is, mass times the gravity. This is the force. And also, the force is same. This is mass density and gravity. The same force, but the energy level is different, isn't it? So here, the potential energy is the mass times gravity times the height of this orange ball. And here, my energy level is less than the first case. The force is the same. And then these, obviously this is in stable position. This is in equilibrium, but it's in unstable position. And how about the second problem? So I have a step here. That I can put my bike here and also here. So obviously the energy level here is smaller than this. And then make sure that these 2 positions correspond to equilibrium positions. There may exist, multiple equilibrium positions. Okay, so let's consider another problem. This is a hairpin. So, this is so-called 똑딱이 hairpin. So in this case, you can open the pin like this. So without, there is no external load. So this is the first equilibrium position. So if you close the pin, this is the second equilibrium position. So make sure that in these 2 cases, there is no external loads, but we have 2 different equilibrium positions. Well, let's consider one more example. So what is one more example? So this is another example found in nanoscale. So recently people are developing stretchable device. Samsung foldable phone is one application of stretchable device. So make sure that if you look at the sensor here, we have a sensor here. Usually sensors are very brittle, and then these brittle sensors are connected to each other using so-called interconnector. Interconnectors made from metal like gold and wires. So to have the potential of deformation, they put this sensor array on top of deformable substrate, and then they stretch the substrate in advance, and they put the sensor array on top of that, and then they release the membrane. Then the membrane shrinks back, and then we have this buckled the connectors. And because of this buckling, we can provide the limited amount of the deformation ability to this device. Okay, still confusing. Okay, let's consider one last example before we talk about Euler problem. Okay, look at this umbrella. Obviously, the weight of the umbrella is fixed, isn't it, right? So if I grab the handle here, is in equilibrium. So even if I provide a little perturbation to back and forth, so you can find its equilibrium position. But what's going to happen if I put my umbrella back like this? Okay, let's put support. Okay, well, let's put support on the bottom of this umbrella. The same gravity load, but to achieve an equilibrium, I have to pay attention to that to keep an equilibrium position. So if I provide a small perturbation in the lateral direction, so it's very easy to lose its stability, isn't it, right? It's an equilibrium, but unstable equilibrium position. Okay, here we'd like to talk about the equilibrium using the famous problem, so-called Euler problem. So Euler discussed the stability or the buckling conditions for this simply supported column. So we have a hinge here, and then I have a beam column, and I have a roller. So we consider the compressive force here. So if you want to understand this problem in the sense of actually loaded member, the stress is equal to P divided by cross-section area, because this is compressive force. That's why the stress should be -1. This is a completely one-dimensional problem. But we already understand the nature of the problem very well. So if you apply load up to a certain level, then we have non-zero finite lateral, the lateral deformation. We already know that. So because this is what. So once we have this deformation, this is not actually loaded member anymore. It becomes another problem. It's like my bike on top of the hill at first. But if you apply small lateral perturbation, it suddenly moves downward. So you find another equilibrium. So this is called stability problem, and the multiple equilibrium. So we'd like to analyze this problem using the actually loaded member, the one-dimensional problem, but suddenly it becomes another category. This is called stability. Okay, so let's take a break here. And then the learning objectives, we want to discuss the basic concepts of elastic buckling, and then we want to drive formulas for the so-called Euler problems. And then we'd like the concept of the buckled mode shapes. And then we'd like to understand the effective lengths of columns if you have different boundary conditions. These are learning objectives. Here we have some advanced subjects, but these advanced subjects are not discussed in the classroom. So we're gonna discuss up to here. So let's take a 5 minutes break.